there is a paper tracing back.
You back the chairship.
Okay, thank you very much. Can you hear me?
Yes.
Okay, very well. So thanks, Catalina, for substituting me. I see that there is Giovanni raising a hand. So I don't know
yes,
if...
I have a question for you, Antonino, if I may.
Yes.
Then I would like to, well, when we start the discussion, I would like to answer Giorgio's question.
I think, I mean, we officially started the discussion session. So your question
when you were disconnected, Giorgio asked the question and I answered, but I had my microphone off, so it didn't.
Okay.
I went on for a couple of minutes, and then you came in, and you took the talk. No, what I would like to say, it's very clear to me that the amplifier, at least in some of these measurements, is the number of systems studied. It's a bit like in proton decay, proton stability studies. But the magnitude of the effect for a single event, for a single system, especially in cases where you envision testing soon quadratic effects, right? That's what you stressed in the end. Even even effects quadratically suppressed by the quantum gravity length scale. What is the, there will be a dimensionless quantity that sets the magnitude of the individual effect. For example, in photon propagation is the product between the Planck length and the photon energy, which is dimensionless. Is here the product of the Planck length and the mass of the system, or the momentum of the system? This is
so here a very good question. A very good question. Let me see if I have in the presentation that I was showing. I should have one slide that should help to answer this question. Actually, this somehow depends on the different experiments that are taken into account. But let me say that if you consider, for instance, the case of Dama, in that case, the energy that you consider is the energy of the distribution, which is a Fermi distribution of the nucleons, okay, which is about MeV, okay. So, and the energy scale is the energy scale that you want to test. So in this case would be the square root of lambda, for instance, and of course the effect will be quadratic in the sense that will be in the square of the energy divided by the square root of lambda square, so lambda. So and this come out directly from the possible transition, as was showing, for instance, in a previous slide. Also Christian. So let's say in this case is the momentum distribution, the momentum of the nucleons. But if we consider, for instance, the case of VIP, in that case is the difference between the K lines and which is order of let's say electron volts, okay. And then, I mean, of course, this change the story, because of course here we are dealing with an energy which is smaller, and of course, I mean, it's the let's say, I mean, from the point of view of the phenomenology, we have the expansion, which is the analytic expansion of that delta square parameter, okay, that was slightly showing. And this expansion, it goes analytically captures linear order that should be the what would come out if considering, for instance, theory that has a parameter of deformation which is linear in the energy. Okay, this is the case for kappa Poincare, for instance. While, for instance, this term would be at the level of the theory of the theoretical framework would be totally missing if you consider theta Poincare case. The theta Poincare case, then I mean that energy would appear as square of the energy, and the scale as we know, has a dimension of length square. Okay, so basically is the theta parameter. So in other way, I mean, it's the energy that appears there can be either a difference of level of energy, or it can be a let's say momentum of the particle that are let's say produced by the transition that are Pauli evaluating, for instance, this emission of neutrons in the case that is considered in DAMA. So it really depends on the experimental situation which is under consideration.
Anyway, not something I should imagine bigger than a few MeVs or something in some of these.
For DAMA is few MeV, yes. For DAMA is few MeV. For the case of for instance of VIP, we are order of magnitude of difference of say K alpha line, so we are in the KEV regime. So it really depends on the particular scenario that is considered experimentally.
I thank you, and it's truly impressive then, the level of sensitivity for quadratic sensitivity to this sort of effect is really striking. I think I'm trying to understand, I mean, there are issues in understanding of these quantum geometries. We understand continuous symmetries pretty well, I would say, Antonino, but we still need to understand better discrete symmetries, like, you know, like those relevant for spin statistics and for CPT.
Yes, yes.
So I'm trying to get a simple-minded physicist intuition for the comparison between the sensitivity of PEP experiments and the sensitivity of CPT tests. And yeah, I guess these numbers are quite impressive on the PEP side, even though, as you know, CPT symmetry is very well tested also. And is also relevant for, is also potentially relevant for quantum gravity research.
I agree, and actually, so there will be in the next day, there will be the lecture by Michele, that we talk about the discrete symmetries, and we connect also this topic to let's say equivalence and entanglement. So that would be extremely interesting to listen as his talk the next time. I would say that for sure the fate of the discrete symmetries is extremely relevant to understand, as you say, the dynamics and to understand, let's say, the physics that is involved in all this discussion. So at this level, for sure, there has been also very much discussion about the deformation of the CPT theorem. Let's say there's been a lot of discussion from a theoretical point of view on theta Poincaré, and as far as I know, also, I mean, it's a lot on kappa Poincaré, mainly, I mean, it's by the Rome group when you were in Rome, now is Napoli group, but also, I mean, Kowalski-Glickman, and I mean, it's the Polish groups. And you're right that, I mean, it is extremely relevant to understand this fate. So I would also say that something that I didn't mention, but I mean, actually I mentioned, but I didn't comment too much, is the importance of considering as well some dynamical that eventually could be also cosmological or astrophysical implementation of deformation of the symmetry that can eventually be relevant at some scale that are the one that are close to inflation, so to say. So at this point, I would say more cosmological than astrophysical, of course. And at that level, we can even consider that condensation and evaporation of condensate can actually also provide a situation, a scenario in which the propagation of particle is, let's say, deformed. So this dynamical breakdown of the symmetry is also another scenario to be taken into account eventually. And that is where I think that having the possibility to cross-check this scenario with the formation of the statistics.
There is a asymmetry between this Rindler vacuum and the Minkowski vacuum, right? So, like,
Sorry?
even if there is a asymmetry between Minkowski vacuum and Rindler vacuum.
Mm-hmm.
So, like, even if there are no particles in the Minkowski vacuum, but an accelerated observer would see some kind of particle density in the his own reference frame. So Rindler vacuum, in that sense, would give you some transverse component of velocity of the particles.
Yes, this is also another interesting way of looking at this. In a certain sense, this is connected to the dynamics. Yes, Giorgio?
Yeah, this is related. The question that I was asking before was about general covariance. And this one, I mean, this theta object transforms how between Minkowski and Rindler, for example?
So the point, okay, so the point, I mean, it's, I think, I mean, it's here, I mean, it's, I will start, let's say, I mean, saying something here, and then after, of course, I welcome Giovanni as well to come back to this point. When we consider, let's say, the introduction of some invariants, of new invariants, what we do is we deform the symbol in such a way to introduce these new invariants. So let's say that the idea of having some background theta tensor is indeed that these objects is now can be considered to either transform, and then I mean that's in this sense break eventually the covariance, or we can think the new symmetry that emerge that stabilize the deformation and the transformation of this tensor, exactly in the same way as we introduce an energy scale which is new now, and set up let's say a new invariant, and this new invariant is actually is also the meaning, which is actually what makes this invariant relevant from a physical point of view, of a new energy scale, which is the case, for instance, of kappa Poincare, or which is the case. So as Giovanni was showing, in a certain sense, if we start considering the Galileo symmetry, basically we don't have a velocity which is an invariant. We don't have a velocity of light. We don't have anything that should set somehow some requirement about the symmetries. But then we introduce it in the Lorentz symmetries, and this change the situation physically. If we introduce a further energy scale, okay, which is basically the Planck scale, or some scale of energy that is connected to some ultraviolet completion of the model, then I mean it's what we're doing. We are requiring that the system should let this symmetry, let the scale to be a new invariant of the theory with the physical meaning, which is let's say recovered when, for instance, we set up the Planck length to go to 0, or the Planck energy to go to infinity, at the same way as the velocity of light go to infinity if we want to recover the Galileo symmetry. Giovanni, you want to say something about this point?
Yes, I I could add this observation that, well, right now we are still looking for a new notion of general covariant theory. So the hierarchy I'm thinking of is you have maximally symmetric spaces, okay, and then you in some sense it's a bottom-up approach in the sense that you first try to understand geometric properties of maximally symmetric spaces, and then the rest. So right now, and it took some 20 years, maybe 30 in some directions, we believe we start to understand this deformed notion of maximally symmetric space. They are maximally symmetric, but they are symmetric in a new sense, in this quantum group symmetries that Antonino was describing and I was implicitly referring to. So the comparison right now, you have to do it at the level of comparing, if you want, maximally symmetric solutions of general relativity. And we think we have candidates for maximally symmetric solutions of quantum gravity, candidates, hypothetical candidates, to be tested experimentally. And indeed, it is a question that we have been asking, and there has been work on quantum group versions of diffeomorphism transformations and all that, but so far nothing really compelling in my opinion. But the question is, what I would ask is not, this is not generally covariant, is what sort of new generally covariant geometrodynamics would admit such spaces as maximally symmetric spaces. But we are going bottom up. So because
that question, no, that is a good. I mean, I have a sort of phenomenological question about this. That the generators that Antonino showed make it inevitable that the notion of inertial mass gets deformed, right?
In some cases,
inertial. Is there a good reason to think that the gravitational mass gets deformed in exactly the same way?
we need, it's a very
You
good
see what I
question,
mean?
and the question we are thinking of is the equivalence principle going to also be affected? But we can only go by heuristics at this point, because we would need the theory we're missing to ask these questions. We don't really have gravity. We have curved spaces, so we can catch the little part of gravity, which means to curve a space. But like in De Sitter, a maximally symmetric curved space, we see the gravity of De Sitter, meaning, you know, gravitational redshift and all sorts of things. But we don't have, you know, geometrodynamics. And that's where really you would feel you would have the tool to, but surely your question is one that is very clearly in our mind, also because, as you know, experimentally is also very well tested. So if we could have,
exactly.
Yeah, of course, yeah, if we could have a clean prediction for some tiny difference between inertial and gravitational mass, that would open another big game. But yes,
Let's say that in a certain sense, I mean, I agree with Giovanni that, I mean, this is a very fundamental question. In a certain sense, let me say that also the possibility of testing different channel for possible deformation of the statistics, or for possible, let's say, Pauli exclusion principle violating transition, is a way to go checking the equivalence principle itself, because, as I was partially saying before, different coupling of the B fields somehow can be realized with the matter fields, and so means we are not completely sure that a democratic scenario is the only possible one in quantum gravity. Of course, as Giovanni was saying, I mean, we lack the theory of quantum gravity, but we have several, let's say, attempts. We have several big framework that we can consider. And in string theory, for instance, I mean, it's the B field that can couple in different way with the matter field. And so let's say that again, we can look at data and we can check if different channels still somehow reject these possibilities. For the moment, of course, or they all reject. So the Pauli exclusion principle is always very well protected. But let's say that is important to improve the sensitivity on all the channels, because these improve also our knowledge of the situation for all the different, let's say, cases of interaction under studies. So a point that I would like to ask a bit to everyone is also where do you think that the next, let's say, generation of data that arise from astrophysical, let's say, experiment, let's say from astrophysical observatories, can be improving our knowledge of, let's say, possible deformation of the Einstein symmetries. In this sense, I would like to ask Giovanni, what is the current status for checking, let's say, the linear or quadratic deformations, both using different kind of probes, and if recent studies and recent experiments, like for instance here in China, LASO, are providing a big, let's say, improvements for this point of view.
Well, I can surely comment, if you want, a little bit on how the LASO results could be, well, one of the ways. I don't, you know, we will learn in the future. Many ways there are, but one of the ways in which they are relevant for some of the topics which are discussed here, and this is some of the same mathematics that, for example, myself and Antonino discussed today, might also lead to a change in the absorption rate of astrophysical particles by the cosmic background. You can recalculate the threshold energy. So, for example, because of the CMBR, you can easily see this. Because of the CMBR peak in the background, photons of 1,000 TeV or so, or a few thousand TeV, get quickly absorbed by the background. So we speak of opacity of the universe, because certain high energy photons cannot reach us from very far, because the cosmic background is like how can I say, it's opaque. It absorbs this photon, which basically is just a quantum mechanical process. It's a collision between this hard photon and one photon in the background that produce an electron-positron pair. And so you lose the high energy photon that you wanted to see from a faraway source. So the fact that LASO could see such high energy particles, it's unfortunate they couldn't establish the sources, the distance of the sources. But surely at least promoting, providing some encouragement for this area of research, because it's surely going in the direction of a universe being less opaque. It's inconclusive, I repeat, because if you don't measure the distance of the source, you cannot make definite estimates about the opacity that you are inferring. But the fact that you see such high energy particles, potentially from rather far within our galaxy, is certainly of encouragement about this whole area of research because it's going into the direction of suggesting that something is affecting the opacity of the universe. This opacity, which is due to the fact that we have these background photons, off of which high energy photons can scatter, essentially producing electron-positron pairs. And then this laser result provides, again, in this limited way that I stressed, provides results which are in some ways consistent with what is coming from another area of research in astrophysics, that is the opacity of the universe to photons of a few tens of TeVs, so lower energies. At those energies, the background which is relevant is the far infrared background. That's where they would scatter they would be absorbed, producing electron-positron pairs. There, the opacity of the universe is surely much less. This is too less discussed. It's a real crisis in astrophysics. The opacity of the universe is much less than expected 15 years ago. Now, one possible answer is that the estimate we made 15 years ago for the far infrared background were incorrect. Because of course, the opacity depends on the density of the background. If you have a very dense background of such soft photons, high energy photons don't travel very far, but if it's less dense, then they can come farther. So on the, say at 10 TeV, there is a potential crisis, which however, astrophysicists are tending to attribute to an incorrect estimate of the far infrared background. Far infrared background is very difficult to measure. The laser observation are shifting this potential crisis to the CMBR background, the 3 Kelvin background, which is much better measured. So let's say that at least in that sense, this new season of astrophysics is probably providing us a chance for some very striking findings if things work out the right way.
Thank you very much, Giovanni. I would like also to ask our other friends who are connected to share their comments on the discussion that we have introducing today. Is there any comments or any question that you would like also to pose to the attention to everyone?
Just, can I just ask, is there, I mean, you talked about forbidden atomic transitions and of course, astrophysics tests. Are there tests from statistical mechanics, from the fact that Fermi surfaces in condensed matter physics are ubiquitous and involve billions and billions of fermions, superconductors and such? This doesn't exclude, this is not as good as forbidden transitions at excluding violations of Pauli exclusion principle.
So let me see if I understood your question. So you're saying that
Fermi Dirac statistics.
Yes. So basically you're saying that yes, I got the point. So basically you're saying that similar situation should be achieved in other contexts. So let me say that what makes here the situation to be very much controllable is the fact that if there are, let's say, transition that are polyviolating, polyforbidden, can actually be recovered because of the control on the radio purity that we have in this experiment. So, and it is a control which is extremely high, because of course, I mean, we suppose that these things to happen should be, let's say, I mean, it's the time scale, as we were saying, were pretty much low. I mean, we're talking about 10 to minus 60 order of suppression for this kind of transition in order to happen. So let's say that for sure, in principle, what you say is possible, but we should have a situation also of multiplication that should happen of critical mass and control of the situation in order to have data which are also as much as net.
The data would be just as a clarification. The data would be the heat capacity and the electric conductivity of superconductors at a few degrees Kelvin or something like that. I mean, this has been measured a lot.
For sure, this has been measured a
To
lot.
high precision, yeah.
Let's say that for sure it has been measured a lot, but I mean, the point is this entailing a critical mass which is comparable to the other cases that we have been considering here, in the sense that, for instance, Borexino, we are talking about 20 kiloton of liquid scintillator, and I mean, are these experiments involving 20 kiloton of material? With is this a 20 kiloton of for the superconductive effect? I mean, I don't know. Like, this is a good question. I mean, we can think about that.
Yeah.
I would say that, I mean, it's the critical mass is the point, is the amplificator.
Okay.
So in principle, what you say is true, but I mean, it's then I mean we have to achieve it. Let's say it's like to say that no, like we have a superconductive effect. Here in Shanghai, the train that goes from the maglev station, let's say, in the city center to the airport. The point is that, of course, to build it from Shanghai to Beijing is a little bit expensive even here in China, and so we have only the 60-kilometer things. But of course, I mean, it's like with the improvement of the technologies, it would be possible one day to have less pricey things. So for probably, I mean, it's I think, I mean, it's your question definitely makes sense, but for the moment, I mean, at least I don't see. But I mean, I'm not an experimentalist, so I think, I mean, it's we have to keep this an eye open on this possibility. So any other comment? Otherwise, I mean, I would think that since we skip the break and there's no end, some of us had to leave for other meeting. I would say that we could also call this first day, and
I think we can test for like we can look for this signature of this non-commutativity of commutativity of this space in the this lamp shift of a hydrogen atom, because if we consider that, then maybe the more precise measurement of lamp shift can reveal some corrections to the lamp shift, so that we can derive from this non-commutativity of this space.
Yes, actually, thank you very much, because this has been done in the past, and there are some references at this point. I think Sheikh Jabari has been doing that for the Theta Poincaré case. The limits, though, were not so constraining, like for instance, what we have been showing here. But you're right that, I mean, that is, for instance, another channel. So let me see if I can quickly find it on my laptop. But otherwise, I mean, it's I will definitely come back with this next time on Thursday, when we have the second round. So it's a paper, it's actually a pretty much old paper. So about more than 10 years ago, probably even almost 20. And I remember that it was suggested was exactly what you're saying. So, but the point is that I mean, I don't know from that day there until now what has been let's say, if there have been some huge breakthrough in the precision. Probably yes, I don't know. So probably, for instance, the analysis could be repeated with new data. So this is a good point, actually. Yes, I agree. This is a good point. So, okay, I don't find the reference, but I mean, I will look for it, okay? And next time we'll point it out so that we can further comment on this point. Thank you anyway for bringing this.
Okay, thanks. Thanks.
Any other comments? Otherwise, I mean, that's all the day for today. Okay, so then I mean, it's again, let me thank you all very much for being here, and we are going to have another let's say second day of this workshop, not tomorrow but the day after tomorrow, always same time slot, so 3 p.m. Brussels time, which is 9 a.m. in East Coast time, 6 a.m. Sorry for reason the West Coast, but it's 6 a.m. there, and 9 p.m. here in Shanghai in China. So thank you all very much, and see you in let's say 48 hours more or less, actually 45. Thank you very much.
Thank you. Thank you for